Healing Hands Health Society presents Dental Webinar Series. We have planned a series dental webinars to keep you abreast of current practice. This series on prosthodontics will be via Zoom, Facebook Live. Presenters are drawn from dental schools in the USA, private practitioners from around the world. To register for future webinars, visit www.hhands.org/dental-training. For future inquiries, contact Facilitator.
Dr. Berna Saglik received a DDS from the Marmara University in Istanbul, Turkey, and a master's in prosthodontics from the University of Michigan School of Dentistry in 2007. Upon graduation, she started working as a full-time faculty member. She is currently teaching in the graduate prosthodontic clinic as well as directing removable partial denture course for sophomore dental students. She's also the co-director of the Dental Postgraduate Program in Prosthodontics. She has received numerous teaching awards, including Dr. Paul Gibbons Award in 2010 and the ADEA Council of Students Residence and Fellow Junior Faculty Award in 2011. She also has been an alumni of the ADEA Leadership Institute. She's a member of the American College of Prosthodontists, American Dental Education Association, and a fellow of the International College of Prosthodontists. She has published several articles in peer-reviewed journals and in areas of advanced prosthodontic procedures and dental implants. She maintains a clinic scheduled in the faculty clinic. Dr.Saglik has been here before, and it's an honor and a privilege to have you. Take it away, Dr. Saglik.
Thank you, Dr. Yuval, for your kind introduction. It is my honor to be here. So I will. So this time I'm back with a little bit more unconventional, more current updates on the removable partial denture. So we're going to be talking about the removable partial denture and CAD prosthodontics. So again, I want to thank you all for zooming in on a Sunday. So it is my honor and pleasure to be here today. So part of this presentation, I'm going to be talking about how that CAD/CAM technology in the removable partial denture treatment is currently used. We'll review some pertinent literature to look at the accuracy of the steps of the removable partial denture from a digital perspective. And then at the last part of the presentation, I'll go briefly about the future directions. So what is a digital removable partial denture? So currently, if you look at the Glossary of Prosthodontic Terms, published in 2017, the 9th edition, the digital denture, whether it's a partial or a complete denture, refers to an appliance, a removable appliance that is created by using the computer-aided design, computer-aided manufacturing, and computer-aided engineering instead of a conventional process. So the slide shows a digital denture and a digital partial denture. The major difference right now at the current process of the digital denture versus digital removable partial denture is in the digital denture process, as the prosthodontist or the general dentist, you are more involved in the whole process and using the software and the steps. So in other words, that whole digital denture process really have altered the clinical steps and either changing either the numbers or the tools in the system. Whereas the digital removable partial denture, it is not as popular currently. It's because it really applies to the laboratory procedures. So when we mean by the digital removable partial denture, having a one piece produced by the digital process is currently not available, but the framework itself can be produced by the digital process. And having that, then really the softwares are more directed towards the dental laboratory versus the clinician. So there are three pathways going into the digital RPD framework. The first one is going to be a partially digital, which means you're going to be taking a conventional impression after you're doing your surveying, designing, and teeth modifications. And then once you send that along with your design, the laboratory is going to scan that impression and then design it digitally and then fabricate it. Again, the fabrication process itself has different methods, but the clinician part is going to be, throughout these steps. You could also, as a partially digital method, you could also pour up your model, and then the model can be sent along with your obviously design information and your work authorization to the dental laboratory, and they would scan your model using a dental scanner, and then they'll use the softwares to design the RPD based on your information and your instructions, and then they'll fabricate the framework. You could also, in the fully digital method, in a way, as again, what I mean by the fully digital, your final process of the RPD still has to be processed conventionally, but the framework, we're talking only about the framework portion here. In the fully digital method, you can do an intramural scan and send that scan to the dental laboratory, and they can do the design on that scan, and then they'll fabricate it and send it back to the printed model. They could also, sometimes, from the intramural scan, they will print your model, especially if they have an older version of these softwares. And especially for the maxillary ones, they might have to do the beading. And if that software doesn't allow them to do the beading on the scanner, then they have to print a model, do the beading, and then they'll have to scan that printed model and then follow with the design. So again, there's like 2 steps that might be just reverting back to fill in that gap for that. So once you get to the design, how do you fabricate it then? There's a direct method of the digital fabrication, which will be using the selective laser melting or selective laser sintering methods, and it will be printed, and we'll talk about that later, and that will be the direct. So there's really no casts anymore, no casting, no finish. Like the finishing is still going to be there, but there will be no screwing, no casting, no investing with this method. And there is also a good number of them are still being printed in plastic. And then the laboratory will get that printed plastic pattern and follow the conventional casting methods. So there is we call that method as an indirect method. And so again, the only gain from the dental laboratory standpoint is basically cutting down on the time that they spent on waxing and duplicating the cast, but really the time that they invest for the investment and then the casting process is still there. So, but there are a lot of labs that still use this method as well. So there are a lot of softwares available from the digital design for the RPDs. It actually started with the first software that you see on the upper left side of the corner. It came out in about 2003-04, and it was a haptic software, and it was by Sensible Technologies, and then later on they were bought by other companies. And then later on, there are other softwares came out by Dental Wings, 3Shape, Amin Görbach for Germany. So, and these softwares kind of like stayed away from the haptic device, and they're more like a mouse or like a touch screen design. It's just sometimes easier. I have tried the haptic device. It takes a learning curve because you're feeling the model. But again, because of the learning curve, my assumption is a lot of these companies went towards the actual the mouse and the or the touch pen or the touch screen design method. But the main idea in a lot of these softwares is to, once you have a STL file, either your intraoral scan or your scan of your model, then they go through the process of setting the path of insertion digitally, checking the undercuts and measuring the undercut digitally, and waxing and designing the whole framework step by step digitally. So everything is basically done on the software, and each of these softwares is going to have their own color coding. They're going to have their own acronyms for the components, but the idea is really just putting all the components together in the digital world. So when we talk about the digital RPD, it actually, as I mentioned earlier, it starts with taking an intraoral scan. If you go to the fully digital way, and that's, I think, where the world is going right now, with all these scanners being available at almost most of the dental offices now. However, there are some limitations for the intraoral scan from a partial edentulous perspective. The first, and as you look at the accuracy of the old intraoral scan, whether it's the partial edentulous or a single crown, the literature talks about 2 things from an accuracy standpoint. They have to be true and they have to be precise. What that means is when you make a scan, it has to be as closer to the original measurement as possible, which we talk about the trueness standpoint. And And every time that you do it, you have to get the same result, which means it has to be precise. However, as I mentioned earlier, there are limitations in a partially edentulous arch that makes this trueness and precision harder when you do an intraoral scan for a partially edentulous. The first one is, as you can see in the slide, is you're trying to take an impression of the soft tissues as well as the hard tissues. And we know by the literature and our clinical experience so far with the scanning, intraoral scanning, taking an image or an intraoral scan for a soft tissue is just challenging. And as we know, and that it really relies basically on the stitching of the images. And as you go into the soft tissues, that stitching of the images is hard because you don't have a reference point in the previous area to be able to stitch it. So that's one challenge when you think about the removable partial denture intraoral scanning. And then we'll take a look at the literature, what the literature says. Now, obviously, the other hard part is our appliance is a one-piece appliance that will be seating on multiple teeth across the arch. And we know that the digital scanning, because of the stitching of the images, creates another challenge as we go across the arch. So the cross-arch accuracy in digital intraoral scanning is also a challenge, whether it's a full arch implant or a partially edentulous. In partially edentulous arches, especially if you do your scan for a partial denture treatment, you're going to be scanning different surfaces with different materials, restorative materials or dentin or enamel on it. So their reflection in the scanner is going to be different. And so that adds another challenge to the intraoral scan of the removable partial denture. So your substrate, again, is different, as I tried to say. And then the last other challenge is, as we do the intraoral scan, obviously we're also going to be recording. If you want to go to the fully digital and model-less approach, then you're going to try to get the intraocclusal record. And when you have less number of teeth, the software is also challenged. There's another challenge in the software to be able to get an accurate intraocclusal record in a virtual environment. So again, these four challenges are existing in the removable partial denture intraoral scanning, and let's take a look at to see what the literature says about these challenges. So the first one, as I mentioned, is that getting an impression and of the edentulous area. And with the partially edentulous, it is not so much as taking intraoral scan for a completely edentulous patient because you still have teeth, so stitching of the images might not be as much of an issue. But you're going to be dealing with an area of the hard palate where you might not have a lot of reference points, as well as a long span edentulous area. So this systematic review in 2019, they actually systematically reviewed the current literature on the accuracy of digital technologies, scanning of the facial, skeletal, and intraoral tissues. And what they said is for the edentulous model, the trueness ranged a lot and up to almost 600 microns, 591, and then the precision was almost up to 698. Again, the numbers seem high, but keep in mind, in a regular conventional impression, that accuracy numbers are also higher, but not as much as it is on the digital world. So their conclusion was that even if the current digital technologies are reported to be accurate for specific applications such as single crown applications, the scanning of the edentulous arches are still representing a challenge. And as a clinician, I can attest to that. Part of it is, really trying to get, as the computer stitches those images, it's harder to get a reference point from the soft tissue. And not only just you're trying to replicate the soft tissue, but you're also trying to get a functional impression. You're trying to do the border molding. And if you try to do that while the software is trying to get some still images, it becomes a challenge. So there are, however, reports in the literature, some technique reports that talk about maybe placing some reference marks, such as radiographic stickers, some stickers on the soft tissue, or maybe applying pressure indicating paste and leaving some marks on the soft tissue with that, so the soft computer can go back to those images when they stitch it, so it becomes a seamless approach. But again, it's still, I think, a big challenge from an intraoral scanner, especially that might be more applicable for maxillary arches where you have a lot of hard palate to scan, and in the class 1 situations when you have a long span edentulous areas. And how about when we, as I mentioned earlier, our appliance is going to be a cross arch appliance. It's going to be sitting on multiple teeth at the same time, and our expectation that they all have to be perfectly seated. So, but we're going to be taking an image starting one side of the arch, and we're going to go to the other side of the arch. So what happens when you do that in a cross arch scan? So this article published in 2019 in Journal of Prosthetic Dentistry, they looked at they compared the 3D arch distortion according to the distance from the tooth that you start scanning, and if you go across the arch, what happens? Where do you see the most inaccuracies, and where does the inaccuracy actually start? And for that, what they did is they got a master model, as you can see in the slide. It's a fully dentate model, and they digitized it using an industrial scanner to be able to use that SDL as their reference point. And then they used 4 intraoral scanners. They were actually 2 scanners with 2 different versions of the software, so that they can also look at, if you update the software, does that make a difference? And they also used the dental laboratory scanner, which a lot of the laboratories use to scan your models. And then, once they got the scans, they overlaid them on an inspection software. Geometric Control is a very commonly used software to be able to, overlay your images and do those measurements. And so, part of their, results, what they found is if you look at the left side of where the graphic is, the scanner started on the left second molar. That's what LSM stands for. And as you go to the next tooth, which is the left second first molar, you're seeing that, the graphic, the mean, root mean squares, the inaccuracies start to build up. And if you look at it, especially if you go to the left canine, so if you go across, if you started to cross the arch, if you finish the quadrant and you start to cross the arch, then you can see the differences in the inaccuracies. So it really becomes a lot of significant the moment you turn that canine and go to the other side of the arch. And if you look at it in between each software, the older version of the software, for example, for Trios 2, did worse than Trios 3. So obviously, each software update also has another important play in terms of the accuracy. And if you look at, for example, the dental laboratory scanner, which is the green one at the bottom, it was really standard across the whole thing, which, as we know by now, that the desktop scanner, the dental laboratory scanner to scan the models are very accurate, actually much more accurate than the intraoral scan. And so what they, part of their conclusion was basically the distortion of the intraoral scan, as you can see these images, it starts from the, where the tooth, from the tooth that the scanning starts. And I think it's just part of the nature of these intraoral scans, because you do your initial scan, and as you're moving your scanner across, your software starts to stitch those images. As the stitching starts and you move further away from your origin, you're going to be adding more inaccuracies, and that's just part of this intraoral scanner. And as I said, every time that these scanners are updated, it becomes better. So obviously, it's probably a work in progress, and we might get to a point that we might really get a very accurate cross-arch scan. I don't think that's too far from where we are right now. So again, but part of their conclusion was, from a partially dental standpoint, is intraoral scanners may help prepare a fixed prosthesis within the scan of the within the scan range of the half arch. Again, their conclusion was based on a fix. We're doing a removable appliance, so we might have more of a leeway there. But we have to also keep in mind that our appliance is made of a very rigid metal, which is chrome cobalt. So even if we do have the give, if that inaccuracy is a lot, then our prosthesis might not be fitting properly because it's a rigid appliance, so there might not be a lot of give for that appliance to be able to seat on everything. So, how do we take this to a clinical environment when we're doing intraoral scan for partially dentulous? The recommendation is really to make sure that you follow the instructions, the scanning strategy of your scanner. That is very, very critical. There's a lot of literature that shows that the experience of the operator in how to use the scanner, as well as following the scanning strategy, plays a lot of role in making the more accurate intraoral scan. So if you choose to do the intraoral scan for a partially dental, it is that important that you follow the manufacturer's instructions in terms of the scanning strategy. So how about, when you do the scanning, and for an intraoral scanning for a partially edentulous arch, and your appliance is going to be seating on multiple teeth. So it's really not similar to an intraoral scan for a fix, because when you scan with the fix, you might be only dealing maybe with the core material, maybe the post-core and dentin, but with partially edentulous, you're going to be dealing with a lot of other restorative materials, different types of porcelain, different type of metals, and as well as like dentin, enamel, and even polished or unpolished, because a lot of the times you prepare restings, but you might not polish the surface if you forget to do that. So, how does all that play in terms of the accuracy? When you do the scan, is it the same on every restorative material? So this group out of South Carolina, Dr. Dutton, and you can see the names, Dr. Ludlow, he's done a lot of research on this area. They looked at the effect of different substrates on the trueness and precision with using different scanners. So because they wanted to take a look, if you use a different scanner, and if you did use a different version of the scanner, does that make a difference? And if you have a different restorative material, does that make a difference? So there was a lot of variables, but I think it was a very nicely done study. And again, it was published in 2019, just very recently. So they got a custom reference standard model. As you can see in there, there's a gold crown, amalgam, polished, there's a core material, there's a dentin, enamel, and there are different types of composites and different types of all ceramic restorations, all in that same model. And then they went ahead and scanned these with using different scanners and even different updates to the scans. And when they evaluated different substrates and the effect they had on trueness and precision, what they found is for many scanners, the more translucent material, such as enamel shaped composite or natural enamel or lithium disilicate, this actually negatively impacted the accuracy, both from a trueness and precision standpoint, which I think is an important finding. And but contrastingly, what they found is more reflective materials, such as polished gold and polished amalgam, did not have much of a negative impact. And some scanners didn't really even get affected by the substrate. So, for example, 303 did not, the substrate did not have an effect on the trueness or precision. So, so what does it tell us? Both from a trueness and precision standpoint, is knowing that, for example, for polished gold, that it didn't really affect. So, we have to really make sure that we polish our rest teeth areas if we place it on these metals. Knowing that reflection really doesn't negatively affect, which is an important finding. And knowing that, some scanners doesn't have much of an effect on, or in certain scanners, the substrate doesn't have much of an effect on the trueness and precision. That might be one thing that to keep in mind if you're trying to find one scanner that has a more broad application. But I think it's an important finding to look at it, especially for a partially edentulous perspective, because of all the prosthetic appliances that we do, it is one appliance that's going to be actually affected probably by this study more than any other study, because your appliance is going to have to sit perfectly on all these different substrates. So then their conclusion was that specific substrate could have a dramatic effect on the trueness and precision. So that's something that we have to keep in mind. And certain scanners are more sensitive to the substrate differences than other scanners. So it's important to know the type of how that your image is acquired by that scanner. And but again, one other thing, that important finding, what they found is the newer generation of the scanners, as you update or as the companies update those scanners, softwares, then it basically becomes a better performance from a trueness and precision standpoint. And I think it's good news on our end, because we do know those updates come almost yearly or sometimes every other year. So what about, as we talked about, the fourth challenge was from an intraoral scan for a digital removable partial dentures was getting an accurate intraocclusal record, especially if you're going to go to fully digital version. So there's the group from Indiana University led by Dr. Wren, Morton, and Lin. They looked at how that intraoral scans and the virtual intraocclusal scans are affected by the number of teeth or the edentulous areas. So they looked at basically whether the span or the location of the edentulous areas affected the accuracy of the virtually virtual intraocclusal record. And especially from a partially edentulous standpoint, as you can see the image over here, they looked at areas where it was a long candidate class 4 cases, like a long span anterior edentulous area. They looked at bilateral edentulous areas, bilateral candidate class 1. They looked at a unilateral, long span, partially edentulous in the posterior region, and as well as simple as a single missing tooth. So in their conclusion, what they found is the span and the location of the edentulous area truly affected the accuracy of the virtual intraocclusal record. So, and as we all know by now that the single posterior teeth was not affected by much, but so that in a complete digital workflow, especially even from a virtual intraocclusal record, is still fully validated. However, unilateral or bilateral extended edentulous area with 3 or more missing teeth. So, as you go a long span, even if it was a tooth bound, if you had 3 or more missing teeth in the posterior, as well as if you had an extended anterior edentulous area, such as in candidate class 4 cases, that the accuracy was affected. So then what they, part of their conclusion was the use of a complete digital workflow in these cases might not be a predictable practice. And we do see that clinically too. A lot of times we still would, even if we choose to do the intraoral scan, we would still do the, you would get the framework, so you get it digital all the way to the fabrication of the framework, and after that you would do the conventional way of like mounting and wax trying and the final delivery. But again, all these softwares are updated, so I don't think it's a long future from now where we're going to get like an accurate, fully digital way of doing for the removable partial dentures. So that was the first part in the digital RPD, doing a digital scanning to be able to get your model. And again, as I mentioned earlier, you as a clinician still have the option of doing a conventional impression and sending it to the laboratory, or getting a conventional impression, pouring up your model, and then sending it to the laboratory. So the second part of the digital, which is really the groundbreaking from a removable partial denture perspective, is that happens at the laboratory where the designing part takes place. So conventionally, as you can see on the upper left slide, we used to, obviously we still do in a lot of the cases, is you would, in your solid model, you would put it on the surveyor, analyze your contours, set the path of insertion, tripod it, and then draw your design. Whereas now digitally, if you look at the right side of the slide, the software would help you to select the path of insertion because you're able to see the undercuts. You see the color coding diagram there that shows the color coded depth of the undercut in every location based on your path of insertion. And again, as you go through adding the components and outline your design, conventionally we used to obviously duplicate this model, and then on the refractory cast you would apply your components based on your design. And that's a lot of times the dental laboratories would do that. It was very rare that clinician would really do the whole fabrication of the RPD because of a lot of the steps that needs to take place, and because of the casting units are not like something that like a gold crown casting unit that you would have at your office. But a lot of that right now is basically the click of a button, and we're going to go through that in mini video to show you how that digital RPD design is done. And then the last part in the process would be from a conventional standpoint, you would add, on the refractory cast, you would add your sprues to get it ready for the investing. So now, even if you choose to do the printing in plastic and conventional casting, the part of the screwing, or at least the support bars, is going to take place in the RPD design software. So a lot of that is really just the click of a button. With the mouse, you can just move forward along the software. It doesn't really take longer. On an average, a lab technician would spend probably 20, maximum 30 minutes in terms of designing the framework. And again, what I mean by the designing, it is not just designing and drawing the outline, it's actually making, in other words, digital wax up of your framework. It's really not a digital design at that point, it becomes a digital wax up. So, as a clinician, just to give you an overview before I move into the video of the design, if you get a partially edentulous case, you will do an intraoral scan, send it to the laboratory. They will set the path of insertion, check the undercuts, follow your design, and outline the framework, and do a digital wax up of the framework. They can send that to you for your approval. which is another important part, probably, even if as a clinician, we're not so much still involved in the RPD softwares. But as a clinician, I think we have the option of being more involved in the fabrication process than we ever did before, because the laboratory can ask for your feedback and your approval before it's fabricated conventionally. So then, we have a lot of option to actually, interrupt in between that process and, direct them to the quality that we ask for, versus previously we would just send the impression model and the framework would get back. And you would basically do a quality assurance at the end result, at the finished product, but now you're able to do the quality assurance at any of the steps that you see. It will come back to you on a model, and then you will do the framework trying. So as a clinician, actually probably the areas that we're involved is the top portion of the slide and the bottom portion of the slide, but the middle portion really happens at the laboratory. So for a lot of the cases. So now let's take a look at this video. So this basically will walk you through how that RPD design is done on the software. So I'll walk you through. So the first step is basically, once you load your model, it will take you to the surveying and blockout. In the surveying and blockout, the blue rod that you see will help you to determine the path of insertion based on the tilt. And at the bottom of it, where you see three different lateral views and a frontal view, so it gives you the image when you choose a path of insertion for your model, the computer will give you three different views from there, to get a better idea, to look from the front, how that angle is going to look like, how that tilt of the cast is going to look from a frontal aspect as well as the lateral aspect. And then the right side of the slide, you're going to see that undercut depth. That's always going to be there as you go through the design portion, because that way you can verify when you place a clasp assembly if you're engaging the undercut. And each software has their own color coding. For this specific software, it starts from the yellow, goes orange and red. But what these numbers mean, basically, if you look at the line between the yellow and the orange, that's 0.25 millimeters, 1/4 of a millimeter, which is exactly 0.010 inch undercut depth that we use in a conventional, a lot of the cast clasp assemblies. The second line that you're going to see is like 0.50, like half a millimeter. So that line is basically corresponds to 0.020 inch undercut, which is mostly what we use for ring clasp assemblies or rolled wire, more like flexible clasp assemblies. And then, as software obviously has 0.75 millimeters, which is corresponding to 0.030 inch undercut, which is typically we would use that conventionally to tripod the cast on the tissue surface. It's almost impossible to get a clasp assembly to be able to flex in and out of it, that much of an undercut. But the software still gives you the idea, let's say, based on your path of insertion. If it was an area that was really deep, you're able to see that. And you're going to see in a second how you get really an idea of the area, not of so much of a point that we used to do with the conventional method. And then on the left side here, you see the direction insertion. So that way you're able to see that. So the next part is basically the blockout. What we're doing right now is basically based on the tilt of the cast. And that's exactly the same way that we would do it on the conventional way, is once you set the path of insertion and the model is blocked out, and then it will be duplicated. So the blockout, whether it's you do a parallel blockout or an arbitrary blockout or a shaped blockout, this is basically based on the part of it. So once the blockout is done, let me just go back a little bit. I just want to show you here. As you do the blockout, you can check to make sure that the undercut is there as you remove the undercuts. Excuse me. Sorry about that. We just clicked on the wrong arrow there. Okay. What I wanted to show you here is as you're checking the undercut over here, as you remove the wax, so the first step is obviously blockout, as I mentioned. Once you do the blockout, and you're going to go ahead and remove the wax in the areas where you're going to be engaging the clasp tips, and that's the area typically where we remove the undercuts from the wax up. And as you do that, you're able to actually click on the undercut area, as you can see on the right side. and you're able to verify that you have an undercut. And now this is the area that I was trying to talk earlier, where you can actually see an area. For example, if you look at the orange area, that tells us we're getting closer to the 0.02 inch undercut, whereas the yellow area is 0.01 inch undercut. So at least as you put your components later on, as you're going to see that you're verifying that you have an undercut in that location where you're going to be placing your clasp assembly. So the next part, and you go into the RPD design as you look at the left side of the slide. The first part is putting the retention grips. And if you look at the outlines, there are different outlines that you can put in a diamond shape. There are open, they call it like a torus ladder, like a lattice design. And you're able to do that. And then the next part is going to be the major connector. So you're at the major connector version, you're going to be first putting the support bar, as you can see at the bottom of it. Especially for the mandibular arch, that usually comes first because you have to outline that inferior portion of your labial plate or lingual plate or labial bar, and then you go ahead and outline the superior portion of your major connector. In the major connector, as you can see over here, let me pause here. If you see the material settings right here, you're going to see like it comes in a standard bar. There's like material thickness. It gives you a substructure thickness. You can choose a so now it's set up like 0.90, so closer to a millimeter in thickness. And then it also gives you the option of if you choose to put any stippling, you know, how many millimeter of depth of stippling you're going to put in there. For the maxillary, you might maybe increase that to give more of a Rouget shape. So, you know, those are things that are all available in the software. So once we're done with the major connector, then we're going to go into the class portion. And in the part of the class portion, the software also lets you outline, do a border on your mesh. And the reason for that, the class portion of the software lets you put things in more like a rod, certain dimensions. So a lot of the times the laboratories, when they design it, when they're going to border their mesh, they're going to use the class portion of the software to do that. And you're able to actually, as you can see, add your tissue stuff at this point too. And and anytime in the software, for any component that you click on, you're also able to see the cross-sectional view and the thickness of it, the height and the width of it. And so that's like an amazing part, because if you think about a conventional waxing, once you put the wax on it, you cannot really measure through unless you ruin the whole wax. So getting a cross-sectional thickness and depth and width of it becomes really, really impossible. And that's why a lot of the laboratory technicians, even if there's still a huge variation in terms of how skilled your laboratory technician is to be able to use these softwares, one thing is still going to come out right is the uniform thickness of all the components, because it is something, no matter how they follow the instructions, it is probably one aspect of the CAD/CAM is, again, the uniform thickness of these components. So again, at this part, you know, once you put the tissue stuff and your outline, your mesh borders, then you can go ahead and choose the clasp assemblies. And if you look in the bottom left here where it says elements, there are different types of the clasp. The software puts different names to it. It is really not the exact same names that we use in the literature. You see it as like a minor C, minor G, and then it becomes a certain thickness. You know, the software also lets you the certain thickness. But at the settings of the software, you're able to actually name them depending on the name you want to use. And you can change these cross-sectional views and the default settings of these clasp tapers, thickness, and the width of it. So a lot of that still, the software gives you a lot of freedom in terms of to customize the taper and the width and the thickness that you feel comfortable with these clasp assemblies. But it does come with like certain standard thicknesses and widths. So again, as you can see, it's really just putting the points, outlining where your components is going to be, and now you just click on the button and it automatically puts those components right where it should be located. And here now you're able to actually see if it engages the undercut or not. And you can, you know, go more like a translucent view so that you're able to make sure that you're not going into the wax in that area. And then you make sure that it engages the undercut. You're able to see, if you do like a scan of the model, you can still see if you want to do the conventional surveying first to make sure that you're doing it right on digitally, and which is a lot of the early learners will do that so that they get used to like maneuvering through the software to be able to make sure that they use the right location and the tilt of the cast. So again, as you can see, these steps will take much longer if you were doing the waxing and wouldn't be as easy to correct it if you did something wrong. And so it really shortened the laboratory time. And that's why it's really becomes more of a groundbreaking from a dental laboratory standpoint versus a clinical standpoint, because clinically we would get the framework no matter what. But the dental laboratory are the ones that really benefited from these softwares. So you're at this point, you can go ahead and smooth out the framework, make sure that the borders look right, and then the components look right where it should be. And then when you click next, now the software is going to join everything together. And then you go into the last two parts of the software, which would be sculpting. So you smooth out the components, and then you add the finishing lines. So here now, after you do the sculpting and smoothing, you go into the finish lines, which is basically now we're putting the external finish line. So this green line that you see, software automatically tells you where the internal finish line is, which is amazing because now you're able to see internally where the acrylic is going to end, so that when you put the external finish line, you're not overlapping them, so they're offset to each other. And now you can also look from an intaglio view. You can remove the model, rotate your framework, and make sure that they're offset to each other, which was impossible to do previously. So again, you're putting the external finish line. You can check the component thickness, the depth of the notch that you place with the external finish line, and you fade it as you come adjacent to the teeth. All the things that we were doing conventionally, or the laboratories were doing conventionally. Again, they're doing it digitally. In other words, the digital software did not really change how you would fabricate a framework, or what are the things that you would look for when you fabricate a framework, but it really changed how you fabricate a framework. So again, you're verifying that this is your internal finish line right here, and then your external and internal finish line are not overlapping. This is one thing that really affects the strength of your acrylic modeling. So that's important thing to look at it. So then as you go to the very final step of the finishing is going to be sculpting the RPD. So now you're basically making the surfaces smooth and blending it. And what you're seeing right now is the areas that we're marking with the red. We can also add beads to add more maybe retention to the proximal plate area where you don't have the acrylic, because obviously our mesh doesn't go there. And what you see right now, for example, a lot of the sculpting area, you will see like a green circle. That's basically the width of your spatula. And as a provider, you're able to change that size of the spatula, the amount of wax that you put on every time that you touch that area with the spatula. And if you look at the wax knife settings, there's a plus sign, there's a minus sign, which means that if you click the plus sign, you're adding wax. If you click the minus sign, you're removing wax. So not only just you add wax to smooth it out, but you're able to remove wax to smooth it out too. So it's basically a digital wax out at this point. And especially lingually, you want to make sure it follows the contours of the teeth. Inferiorly around the border of your lingual bar or lingual plate, that pear shape has to be there, has to be smooth, because we're dealing with a very soft and fragile tissue there, because any sharp corners, any sharp outline there is going to irritate the patient. So now you kind of like see an outline of the final design. So at this point, you can actually, so as you can see, the software designs in different colors, but you're also able to see it in the gray color as well. So you're able to see it in like an actual framework color if you choose to do that, just to get an idea. You can remove the wax and look at the framework and rotate it in different angles to be able to see how it looks internally, to make sure that you can zoom in to look at your internal finish lines, your tissue stop, the internal aspect of your framework to make sure that there's really no sharp corners anywhere. And then you can put your model back on, and then you can also now turn on the undercut gauge and make sure that you're able to see the framework is engaging the undercut. because this is, I think, like a really groundbreaking at this point, because this was something that impossible to do in the conventional method, because once you start waxing, you're not able to go back to the original model to see that unless you finish the whole framework and fit it on your master cast. So now you're actually able to see midway and every step of the way. So again, that's what I was saying earlier. Even if as a clinician we're not involved in the final production or the actual production of the framework, but as a clinician we have a better option of looking at the quality of these frameworks before they are even fabricated. In other words, if you had any reservation of the undercuts, once the lab, let's say, first of all, they can still see it once they start the design, and you're not so sure about if that undercut is going to work with that class design that you chose, they can do the design, send you the screenshot, or they can actually do like a TeamViewer meeting that you're able to see their software as they work on it. And now you can go back and see that before the framework is fabricated, if it's engaging the undercut in those areas. Let's say if your lab has a tendency to make certain components thicker than it should be, you're able to see them at this point and tell them to change it to however you want it. So I think this digital technology really significantly improves that teamwork or the team abilities between the provider and the dental laboratory. You become more connected to your partial denture laboratory than you ever did before. So once you do the digital design, or the dental laboratory does the digital design, then it goes into the printing portion. So again, there are two methods of the fabrication. It's one method is the indirect. So once you do the design, the laboratory will print a plastic pattern, and then they will do the conventional casting and follow the conventional finishing and send it on your master cast after it's fitted. They could also get this digital design and send it to what's called a selective laser melting unit and print it digitally using these technologies available, and then get the framework, finish it, and send it back to you on your master cast. So the direct method, selective laser melting, is becoming more popular because, as you would imagine, it really eliminates that whole casting process, which was another important hardship that we would see in from a dental laboratory standpoint in the RPD production, because as you would imagine, there's a lot of errors that still goes into the casting. So by doing it digitally, obviously you eliminate the time that the dental laboratory invests in it. You also eliminate, in a way, the human power or human time or human resource that you need to do the casting. And be able to do more casting at the same time, because these units really are able to handle more than hundreds of units at a time. And with just the click of a button. So, but the major thing as of right now is the accuracy. So now let's take a look what we mean by the selective laser melting. Just a reminder in terms of what that means is basically an additive, computer-aided manufacturing way. So that means you're not really taking from a block and milling, but you're adding layer by layer. And in this case, usually there's a metal powder or an alloy powder that the laser beam hits. And either it melts it in the metal pool, and then as the computer builds it up, it's basically going to be built layer by layer based on your design. And as you can see in the bottom picture, and then basically emerges out of this pool of metal. Or the laser beam hits to this polymer powder or metal powder, it melts it just enough and fuses together, and that's called sintering. A lot of the times, for the chrome cobalt alloy, it will be the selective laser melting that's been used versus the sintering. Sintering is usually used for polymers that are available for some of these RPD frameworks. So this again just shows you, this is an image from Wikipedia. It shows you that the laser beam over here hits the powder, the processing layer. And if you look at it over here, for example, there's a fabrication piston. So your object that's been fabricated is here, and the laser beam hits that fabrication powder bed, and your framework is built layer by layer as each powder layer is melted. So how are they fitting though? What's the accuracy on these? It's getting more accurate, I can tell you that. And a lot of the inaccuracy that happens from selective laser melting comes from how that metal is heat treated post-production especially for the RPD frameworks, because our appliance is quite fragile in a way that everything has to fit at the same time in every component. And if you don't treat the metal right, you might bend it, and if you bend it, nothing is going to work. But if the heat treatment protocol is followed, and then the finishing is done ideal, a lot of them could turn out accurate. But in the literature, you see a lot of variance in the research that's done on selective laser melting, and major reason is that there's a lot of variance in terms of what machine is used, what type of alloy powder composition has been used for that specific machine, and how that heat treatment is done post-production. So, this study, for example, out of Loma Linda University, is a very well done study. It was published in Journal of Prosthodontics in 2019. What they did is they looked at the overall accuracy and fit of conventional versus computer-aided CAD/CAM RPD frameworks with the and they basically looked at the accuracy and fit of each component: the rest seat, proximal plates, clasp semis, major connectors, like the components within an RPD framework. So what they did is they got a master model, and from the master model they did 4 groups. So they first looked at taking a conventional impression, pouring up in stone, and then doing the conventional casting, which will be the group 1. And then the middle 2 group, they looked at the 3D printed ones, the SLM methods. So they did it, or the group 2, they did that intraoral scan, and then they did an STL file, digitally fabricated using the these SLM, and then 3D printed and fitted to the framework. In the third SLM method, they did a conventional impression, got a stone cast, and the lab scanned the stone cast, and then they did 3D printing. And then in the last group, they did an intraoral scan, they did a printed resin, and then they followed the conventional casting. So again, it was acrylic printed cast that I showed, a printed framework that I showed you earlier. That's what they did for group. And then they made these frameworks, fitted into the model, and then they used like a fit checker similar to that material, placed them on the framework, and then they looked at that thickness of the fit checker and to see the depth of these components and the accuracy of these across the arch. So what they found overall, in terms of the overall fit of accuracies, if you look at group 1, which is the conventional method, it was probably one of the best ones in a way. So the group 1 and group 4 did better than the middle 2 group. So group 1 was the fully conventional, and group 4 was you did an intraoral scan, and the lab printed the model, and did the design, and they printed the plastic pattern, and they casted it. So that group 4 did the best in terms of fit, and the second best was the fully conventional. If you look at the other 2 groups, which are in the middle, whether you did intraoral scan or you did conventional impression, but the framework was fabricated by the 3D printing. And what they found, they were closer together, but there was a big significant difference than the conventional casting. So, and as you can see with the color coding, you can see there is a lot of variations in the B and C images, which are the 3D printed ones. The basically red and yellow to red shows a lot of more space, which means you're seeing more like red on the denture base areas and the major connector areas. And if you look at A and D, which are basically the conventional casting, whether you're doing intraoral scan or you're doing the conventional impression, they revealed a better fit. And especially group 4, there was also a lot of highest amount of tissue compression that was seen. That was one of their findings. But overall, their conclusion was that the conventional process RPD frameworks, whether you did intraoral scan or you did a conventional impression, revealed a better fit and accuracy compared to the 3D printed frameworks. However, the range was still clinically acceptable based on the clinically acceptable numbers that are published in the literature in previous years. And there was really no significant difference in terms of the fit of the 3D printed, whether you did an intraoral scan or you did a conventional impression. So as long as the 3D printed framework was done, there was really not a lot of difference between those 2 methods. And another interesting finding was a high fit accuracy were seen in the areas of rest and proximal plates for all the components of all the frameworks that are made in 4 groups, which is an important finding. And I think because we do want to really have a good internal fit, in the areas of rest and proximal plate, and the literature actually in the long term shows previously in the conventional frameworks, the rest seat contact over time becomes really a major issue. And then the last finding, what they found was the poorest fit was seen around the anterior straps. In the major connector, we did see a lot of like variance in there. And I think it does play an important role in terms of how the impression is made or how the scan is made, again, in the soft tissue areas. And I think that, you know, that part probably plays an important role in terms of that fit. How about clinically? So this was one of the clinical studies. They got 10 participants and either maxillary or mandibular framework. They did an intraoral scan, but they did a 3D printed with the plastic pattern. They actually tried the plastic pattern in this cases on these patients, and then they fabricated final denture, and then they did like a pickup impression and using a fit checker on the internal aspect of the fitting. And they actually, you can see in the B, diagram B over here, they looked at the rest seats, the major connector, even the denture base area. And part of their finding, what they found is really, if you look at it, the minor connector are the best fitting across everything. And the major connector, there were a lot of variance in the major connector. The rest in class, they were still like less than the, within the threshold of the clinically acceptable. And as well as the edentulous area, you know, there was not a lot of difference in the edentulous area. Actual major connector did the worst in this study as well. And then they looked at also specifically on the rest seats to see if the periphery or the center does better. And what they found is the periphery actually does better than the center. And again, I think part of it is also the scanning, how well you're able to record that image of that design that you prepared. And you can see actually there was a lot of difference in the cingulum versus your occlusal rest. And I think that we come back to our cingulum design. Conventionally, we use inverted comber, which creates like a sharp line in the design. And maybe that has something to do with the scanning. This is, again, just my questioning of the study. I don't know the details of what exactly burrs were used for the cingulum rest. But all I'm trying to point out here is, as we do the intraoral scan, we also have to take a look at, maybe go back and look at our designs that we do for the rest seat preparation, to see if those designs that were done for years are still feasible to do an accurate scan if we were doing the digital. So that's something that we have to keep in mind. You know, again, part of their conclusion was the single rest, the accuracy of the periphery was better than the center. So where do we go from here? It opens up a lot of doors. As I mentioned, you know, you could use it in the dental education. That's one thing that, you know, it's becoming more popular, and that's what we're trying to do at the University of Michigan too. And this article really summarizes that clinical need for innovation, that with the digital technology, that a lot of the material that we're not able to use can be used now, because you're able to mill them and print them. So that's probably what the dental technology or dental world is going to be doing right now, is looking into different options of materials that could be also used to replace the metal. And because we know the metal, a lot of our patients doesn't like the metal showing, and some of them might have some allergies to the components that are placed, or the alloy structure that might be used in part of these frameworks. And but previously, a lot of the other material were not able to use, because the material that could be an alternative in terms of rigidity and strength over time were only available if you were going to mill them or print them. But now with the digital, that image or that STL file could be milled or printed. So it really brings a lot of options, opens the doors to new technologies and different materials. And but again, you know, whether you do a conventional or if you use the top of the line software to do the design, it all comes down to how well you know your basics. So it's really not the wand, but it's the wizard in us that makes these softwares and technologies work for the best of our patients and for the best of our treatments. So I want to thank you for your patience, and I'm more than happy to take any questions that you might have. So thank you.
All right. Thank you so much, Dr. Saglik.
My pleasure, please.
Thank you. Someone put a comment here that this is a lot of new information for Nigerian or African, Dr. Oshua, I guess you're speaking for yourself, for the Nigerian, like this is a lot of new information. So I wanted to ask, is there any member of faculty here on the call that if you teach removable partial dentures, if you teach that course and you are on the call, please, I would like to just get your comment. I just want to speak with you. If you are here, just identify, you raise your hand, I'll give you an opportunity to just speak. But I really appreciate, I mean, this is the reason why I guess I am pursuing a course in prosthodontics, because there's a lot of evidence based, it's all based on current, very recent findings in terms of what is happening, and how you compare it to what is working, what is not working. There are new materials coming. You're talking about the use of implants with, that will be another, I guess, Dr. Saglik.
That's a totally different topic by itself. Yeah, but you're right. Like there is another world in removable partial dentures to minimize denture-based movements, use of implants with removable partial denture, which I think is probably one of the best aspects of dental implants in removable partial denture. It really turns into that tooth mucosa into a tooth implant, which solves a lot of the problems that we had previously with partials.
Anyway, I mean, the world is advancing, and I'm really thankful for the opportunity to have.
It is my pleasure. Thank you.
Thank you so much.
My pleasure. Thank you.
We're going to send out a post-test from this lecture. It's going to be available on YouTube, so you can go back. I'll give you an opportunity to just listen to it again, and there'll be 6 questions, Dr. Saglik.
Sure. Yes. Mm-hmm.
Okay. I'll send 6 questions, and it's just your answer, so that at the end of the day, you want to learn something, you want to keep something, you want to retain it, and these questions kind of guide you to concepts. It's not about our pass or fail. It's about you going through the material and picking out the essential points. This is an essential summary of what is the latest information. Thank you so much.
My pleasure. Thank you. Guys, have a good day. Thanks.
So we're going to move on now.
Healing Hands Health Society presents Dental Webinar Series. We have planned a series dental webinars to keep you abreast of current practice. This series on prosthodontics will be via Zoom, Facebook Live. Presenters are drawn from dental schools in the USA, private practitioners from around the world. To register for future webinars, visit www.hhands.org/dental-training. For future inquiries, contact Facilitator